Hi everyone. So we're gonna do a photoelectric effect, which is like a great off topic. Yeah. And we're just going to cover just a brief information about it. Not a lot of information, and going to just do two examples of uh typical exam questions that you might expect for your tests and exams. So what is photoelectric effect? Photoelectric effect is basically the process whereby electrons are ejected from a surface using light. So what you need to know from important things that you need to take note is we have terminologies that you have to know how to define, such as the work function, which is the minimum energy required to eject electrons from a metal surface. It is represented by the equation of W naught, or someone can say WO is equals to H, which is a constant, Planck's constant, and FO, or F naught, is the frequency. That F naught means like it is the cutoff frequency or a threshold frequency. Then we have threshold frequency. You have to define it, and it is defined as a minimum frequency of incident light that is required to emit photoelectrons from the surface of metal. It is like the work function, but here we are talking about frequency, while in the work function we are talking about minimum energy. So what you also need to know is that the amount of energy in a quantum is directly proportional to the frequency of light. That means that a quantum is a certain it's the energy that a photon of light has. So that energy of photon, it is directly proportional to the frequency of light. This means that if the frequency is high, also the energy in the photon is high. If the frequency is low, then the energy in the photon is low. Then we also have to know that increasing wavelength of light means decreasing frequency. You'll notice this on an electromagnetic spectrum. When you look at an electromagnetic spectrum, you see that we have longer waves, which if a light has a longer wavelength, it means it has a low frequency. And if it has a shorter wavelength, it means it has a high frequency. You can see from the gamma rays in the picture that I've displayed, radio waves have a longer wavelength compared to gamma rays, which have a shorter wavelength. This means gamma rays have a higher frequency compared to radio waves, which have a lower frequency because of their longer wavelength. So increasing wavelength means decreasing frequency. So one thing again to note is that we have conditions whereby electrons need to be ejected from the metal surface. Number one is that the frequency of light needs to be greater than the threshold frequency of the cutoff frequency. We said the threshold frequency, it is the minimum frequency needed or required to eject electrons from a metal surface. Therefore, in order for the electrons to be emitted, the frequency of light that is shown into the surface needs to be greater, or otherwise no photoelectrons, or rather electrons, will be released from the surface. But if the frequency of light is equal to the cutoff frequency or the threshold frequency, the electrons that will be released onto the surface of the metal. They will not have kinetic energy, and thus they will not move away from the surface. They will just be vibrated or just be ejected from the surface onto the surface. They won't go anywhere. That but in another case, if the frequency of light is greater, the frequency of the incident light, to be specific, is greater than the cutoff of frequency or the threshold frequency, it means the photoelectrons or electrons will be released from the surface and they will have kinetic energy because the incident light has a higher frequency than the threshold frequency. They will be released away from the metal surface and they will have kinetic energy. This is just a brief information that you will need to know as we continue. We're going to do examples. More information will be done as we go through the questions. The first example that I have is this question 10. So the question says, when light of various frequencies is incident on a metal cathode of a photocell, photoelectrons are emitted from the surface of the cathode, right? The graph below shows relationship between the maximum kinetic energy of the emitted photoelectron and the wavelength of the incident ray. We're looking at the maximum energy, kinetic energy of the emitted photoelectron compared to the wavelength of the incident light. So you can study the graph. You can see, okay, my graph is decreasing. I have points. What about my wavelength? It's increasing from 5, 1, 2, 3, up to 0.5, 1, 2, 3, up to 5 times 10 to the negative 7 meters. This side, my kinetic energy for my photoelectrons is also increasing. So let's look at the first question that they can ask you in an exam. Use the graph to determine the maximum kinetic energy of the emitted photoelectron when the wavelength of the incident light is 1.0 times 10 to the power of negative 7 meters. So you go to your graph, go to your wavelength, your x-axis, look for 1.0 times 10 to the power of negative 7 meters. You use your ruler to trace it. Let's go up. We're looking for the kinetic energy of the emitted photoelectron. Looking at this is the point here. So where it is the point? It is between 12 to the negative 19 joules and 10 to negative 19 joules, but it is not in the middle, so it is likely above 11, since between 10 and 12 there's 11. So if 11 is in between, also the point here is not directly in between 12 and 11, 12 and 10. So you can also trace, okay, where is my point? You can make a trace it to the y, which means it's somewhere ranging between 11.6, 11.7, 11.8. It cannot be 12 because it didn't reach 12. 11.6, 11.7, 11.8 times 10 to the power negative joules. That is a pretty easy one. So we have our answer here. I chose 11.6 times 10 to the negative 19 joules. So the next question says, what is the relationship between the maximum kinetic energy of emitted photoelectron and the wavelength of the incident light that can be detected from the graph? When you look at the graph, in mathematics, you can say this is a negative graph. This is a decreasing graph. So what is the relationship? You're going to use your information that you have here. So when you look at the graph, as the wavelength of the incident light ray increases, the maximum kinetic energy of emitted photoelectron decreases. The graph is decreasing. That will be the conclusion of the second question. Let's look at it. So yes, as the wavelength of the incident light increases, maximum kinetic energy of the emitted photoelectron decreases. That is 2 marks. So we have, just I had mentioned, you have to know the definitions of important terms such as work functions. So here they ask you to define what a work function is. That is energy. Work is energy. So work function, it is the minimum energy required to eject or release electrons from a metal surface. You need to know that. So moving to the next question. The next question says, use the graph to calculate the work function of the metal used as cathode in this photocell. So you're using the graph. So when you use a graph, especially when you're going to use points, you want to make sure that you try and find the points that are the most, if not exactly, precise. So when you look at your graph, you can see already this point, it's almost exactly precise, almost exactly where I wanted. I won't be doing a lot of estimations. It is exactly at 8. It is exactly at 1.5. And you can look for another one. Okay, let's look another one. Oh, this one is below. Okay. Oh, hey, hi. Where the graph ends, which is at 4.9 times 10 to negative centimeters, because it is not at 5 exactly. It is also at 0 kinetic energy for the y-axis. So these are 2 points that you can use actually to calculate the work function, which is the minimum energy required to eject electrons from a surface. So we have a formula that we use to calculate work function if we are given kinetic energy and energy of light. That is energy of light. E is energy of light is equals to the work function plus the kinetic energy of the photoelectrons. Energy of light is calculated using H times the frequency, if you're given the frequency. And also the work function is also, again, because it is energy, again, the minimum energy, remember, also now it is calculated using the formula work function is equals to H times cut-off frequency. Work function is the minimum, so it has to go with minimum frequency, right? So if you decide to use the point that has a 0 minimum kinetic energy, you can manipulate the equation into saying that the energy of light is equals to the work function. So we do substitutions. Planck's constant h, c, the speed of light, lambda, the wavelength. You may ask yourself, where is this coming from? Energy is equals to hf, just like I've said. But what is f? F is equals to speed of light divided by wavelength. So since here we don't have the frequency, we have the wavelength, it means that we have to substitute our F or frequency with speed of light divided by wavelength. Thus, it will give us this part of our equation is equals to the work function. Then from there, you substitute your variables. We didn't include the kinetic energy because it is what? It is 0. So you substitute the values that you have, then you get your work function. Or you can use the other point, that is 1.5 times 10 to the power negative 7 meters wavelength, and 8.0 times 10 to the negative 19 joules. That is the kinetic energy of the photoelectrons. So using the same formula, you work around it and make work function subject to the formula. Substitute variables, substitute f, and then substitute your variables here. Here is the speed of light, 3 times 10 to the power of 8, and your wavelength and your kinetic energy of photoelectron. It will give you this answer. Either of these answers is correct. Then we go to the next question. The next question says, calculate the maximum energy of the emitted photoelectron when the wavelength of incident light is 0.5 times 10 to the negative 7 meters. Where is 0.5 times 10 to the negative 7 meters on the graph? There it is, and there is no line indicating where where you can trace the kinetic energy of photoelectrons. Therefore, you need to calculate it using our formula. E is equals to work function plus kinetic energy. We know the work function. We have calculated it on the above, on the previous question. We have calculated in the previous question, so we just simply have to substitute it. And then E is equals to hc over lambda, just like as I explained where I take the hc over lambda. So you substitute your variables, you are given the wavelength, so you substitute the wavelength and your work function that you have calculated in the above equation, then you get your kinetic energy at that wavelength. Great, so moving on, we have another question, smart questions that you can give you. Make sure that you practice more of these questions. Very interesting questions. So this question says, the relationship between frequency and maximum kinetic energy of photoelectrons emitted from two cathodes, cathode M and cathode N, of different photoelectric cells is investigated. Then the graphs below have been obtained from the results. This is your graph. You see this is cathode M, cathode N. Okay, you can see this is the frequency and the y-axis, and this is the kinetic energy of the photoelectrons ejected. So when you look at these cathodes, you can see, since this frequency it is at definitely like it corresponds to the 0 kinetic energy, it must be like the cut-off frequency or threshold frequency, right? These points to be specific. These 2 points to be specific. So the first question says, define threshold frequency. You need to know these questions. Define threshold frequency, the cut-off frequency. It is the minimum frequency of light required to eject electrons from a metal surface. It is as simple as that. Then the second question says, how does the maximum kinetic energy of photoelectrons emitted from cathode N compare to the maximum kinetic energy of those emitted in cathode M when light of frequency greater than 10.40 times 10 to the power 14 Hz is shown on each of the cathodes? Choose from greater than, smaller than, or equal to. These frequencies are the minimum frequencies needed to eject electrons from a metal surface. Remember, I said frequency is the frequency of light that is shown into a metal surface is directly proportional to its energy, which means if it has a high frequency, it also has a high energy. So for cathode N, the minimum frequency needed to move the electrons from the metal surface is just 5.16. So if I shine a light that has a frequency that is greater than 10, which is 2 times the minimum frequency needed, it means the energy that I'm transferring into the plate, the metal plate, the metal surface is 2 times what is actually needed. So the kinetic energy of the ejected electrons will be definitely 2 times higher than the minimum energy that they would have had after being ejected using this frequency. So the ejected electrons at cathode N, they are at a kinetic energy that is 2 times greater than a minimum energy that they would have had if this amount was just shown into the metal plate. Then we have cathode M. Cathode M needs a minimum frequency of light that is 2 times that of N to move and eject electrons from cathode M. So if I shine light of frequency that is 11 or 12 hertz on this cathode, they are going to be ejected from the metal surface, yes, but at their kinetic energy will be relatively most likely to be lower or not as much as high as they would have liked. It will not be at their maximum and super excited electrons, because they were only just given a minimum energy to move. So they will just move, okay, we are just moving. So when you compare these two, definitely the kinetic energy of electrons ejected at cathode F, it is much higher than the kinetic energy of the electrons ejected at M. I hope you can get it. So our answer here will be greater than. So moving to the next question, it says calculate the frequency fx indicated on the graph. Fx indicated on the graph here is fx. So fx, when you look at fx, it is like corresponding to cathode M. It is the y-intercept of the value at cathode M. So which means we have a kinetic energy. We are given the kinetic energy of the ejected electrons at this frequency. So what we need to do is just use our formula. Energy of light is equals to the cutoff work function plus the kinetic energy of ejected electrons. So we substitute E with Fx, the energy of light. We substitute work function with H, F, cut FO, F naught, cut off frequency, plus E, EK, kinetic energy. Substitute the Planck's constant. H is constant, so you will always be given, or rather have to know, that H is 6.63 times 10 to the negative 34. Do direct substitution. Work function goes together with cutoff frequency, the minimum frequency to eject electrons, which is what we've been talking about. This here, this the y-intercept here, it is the minimum frequency needed to eject electrons. That is the cutoff frequency. Substitute it for F naught and substitute the energy 23 of energy, kinetic energy of the ejected electrons, then solve for Fx. That is the frequency that you are looking for. This is the frequency of light that is shown into the metal surface. Then the next question says, the experiment is now repeated for cathode M using the light of frequency Fx that we just found, but a high intensity. But of high intensity, it means that intensity means brightness, basically. It means the same frequency is used, but now we're using it, the light is brighter. How will each of the following be affected? Choose increase, decrease, or no effect. Now, the first one is the y-intercept of the graph. How will the y-intercept of the graph be affected? The y-intercept of the graph is the frequency of the light. So it does not, they do not interact. The frequency of the light does not depend on the intensity of the light. So there is no effect on the y-intercept or the cut-off frequencies of these, or rather the cathode M. The number of electrons emitted per time. Now, this is different. Intensity brightness only affects the number of electrons and charges that are the number of charges, photons of light that are ejected, that are shown into, are transferred into the metal surface, and the number of electrons ejected from the surface. So if there's high intensity brightness, it means there is a larger number of photons that is ejected into the surface, and thus, therefore, there is going to be more photoelectrons that are going to be ejected from the surface. Thus, it affects it as like more. If there's higher intensity, there's an increase in the photoelectrons that are emitted from the metal surface. The next question, the maximum kinetic energy of the emitted photoelectrons. Maximum kinetic energy, remember, the energy is directly proportional to the frequency. High frequency, high energy. Low frequency, low energy. So firstly, we said intensity does not affect the frequency, or it is not affected by the frequency of light. Therefore, if the frequency of light is not affected, therefore the energy, the kinetic energy of the emitted photoelectrons will not be affected. Thus, the answer is no effect right here. And that will be all for now. Please practice more questions. I'll be back with more interesting information about this topic. And good luck. Thank you.